Hello. So today I wanted to talk a little bit about Venturi effect and its application in it can have multiple applications in many medical or biomedical applications, and non-biomedical applications. It's a very interesting phenomena which occurs, which helps you to measure flow. It can also help you to create vacuum, also to measure velocity. Its applications are very widespread. So let's try to understand what Venturi effect is. Okay. So to understand Venturi effect, we need to understand Bernoulli's principle first. Okay, so let us say I have a I have some tube like this. Okay, and it is closed at both ends. It is closed in both ends. Okay, so and suppose this has a pressure P here. Okay, what do you think the pressure? Suppose this is pressure P1. What do you think is the pressure P2 here? Okay, can you guess? So here pressure P1 equal to P2. If there is, so in static case, so if there is no movement in fluid, so in static case, pressure is uniform throughout the structure. Okay, the structure can be like anything. The structure can be something of this sort. If the fluid is not moving, if the fluid is not moving, the pressure is same throughout the structure. Okay, because the basic idea is the fluid movement only occurs in a pipe when there is a pressure difference. So that means if there is no movement, there is no movement of fluid, that would mean that there is no pressure differential. Okay, now the interesting thing happens when we have actually movement of fluid. Okay? When you have a moving fluid, for example, suppose this is a, just let me show something here. Okay, suppose I draw some structure like this here, and pressure here is P1, and water or some fluid is moving into this at the velocity of V1, and here the pressure is P2, and water is moving out of this point at velocity V2, and the height difference, suppose this is the ground level, this is the surface level. From this surface level to the center of this point is h1. This height is h1, and suppose from this point to the center of this tube here, the height is h2. Okay, now in this case, what we apply is, and so and the area here is, area is a1, area of cross section is a1, and area of cross section here is a2. Okay? Now the amount of fluid which moves in per second, because this is given in meters per second velocity and area is in meters square. So overall the volume of fluid which moves into this tube per second is should be equal to the volume of fluid which comes out of this tube per second. So volume which enters per second into this tube will be given by A1 V1, okay, which is meter cube per second. This has to be equal to A2 V2. Okay, so this is the these are actually velocities. Okay, V1 V2 are velocities. A1 V1 is the volume flow per second. and E2 V2 is the volume outflow per second. This is volume inflow per second, this is volume outflow per second. So volume inflow should be equal to volume outflow. This is the continuity equation. This is called as the continuity equation. If this equation doesn't hold, that means water is getting either sucked out of vacuum, means water is getting accumulated inside the system, which is not possible. If water starts getting accumulated here, if water starts getting accumulated, this pipe can burst. Okay, so A1 V1 has essentially should essentially be equal to A2 V2. This is the continuity equation. Then the other equation is the energy conservation equation, which is given by the Bernoulli's equation. Here the formula is E1 plus rho g h1, which is the potential energy. Okay, potential energy at um, the potential energy here from this point, plus half rho v square, which is the kinetic energy of the water. Okay, and this is the this is also represents the energy which is due to the inflow pressure. Okay, so this has to be equal to, this is v1 square, this has to be equal to v2 plus rho g h2 plus half rho v2 square. Okay, so this is your Bernoulli's equation. So by using continuity equation, which is equation 1, and Bernoulli's equation, which is equation 2, we can solve for many different conditions. Okay, where suppose we want to know what is the flow velocity at a particular point in the tube, or we want to know what is the pressure at certain point in the tube if other parameters are known. Okay, so based on this, the Venturi tube, we will try to understand the principle of a Venturimeter, which is used to measure the flow velocity, okay, of a fluid. The Venturimeter, the way it looks like is Venturimeter basic construction is given like this. So you have a larger entry point, and then you have a tube like this. Then you have a smaller entry point like this, and you have on the outflow or a kind of socket out of this tube like this. Then this tube again comes back to the original size, this side. Okay, so this side the pressure is P1 and the area is A1 and the velocity of flow is V1. This side also the area is A1. Pressure of course automatically becomes P1 and velocity of outflow is V1. So this is a meter which can connect to a pipeline without changing the pressure velocity relationship from the inflow to the outflow. Okay, but there is a change in the middle of this tube where the tube becomes thin. Okay, here the area is E2 and the pressure is say P2. Okay, now suppose there is a fluid which is flowing through this tube. There is a fluid which is flowing through this tube. So because of this fluid flowing, what will happen is there is a pressure which is built up here. Suppose because of that the fluid, this is basically the fluid, that fluid also rises a little bit on the tube here. Okay, and so this distance here from this point to this point is the is given by say hv, okay, which is the height difference between these 2 points. Now we want to find out what is velocity. Suppose we know pressure P1. Suppose you know the area A1 and A2. Of course, you know the area A1 and A2, and we want to find out what is the flow velocity, okay, V1. So for this, we can apply our first we'll apply the Bernoulli's equation. Bernoulli's equation will be given by P1 plus half rho V1 square is equal to v2 plus half rho v2 square. Okay, this is Bernoulli equation. The height, there will be rho gh, but rho gh1 is equal to rho gh2. So if I put rho h on this side and rho gh on this side, both of them get cancelled. So that's why I'm not putting rho gh on both sides, because the tube is having the thinner tube and the lower diameter tube and the higher diameter tube both are at the same height from ground. So this is how you have to maintain the tube. You cannot have the tube set, you cannot have the tube set vertically or in some angle, because then this equation will not be valid. Okay, so this tube has to be parallel to the ground. Now, so this is, here the velocity is v2. So this is the formula which you are applying for this. Now, from this we can apply. You can do p1 minus p2 is equal to half rho v2 square minus v1 square. v2 square minus v1 square. That implies um, now p1 minus p2. Now this p1 minus p2 is equal to, if I look at this h nu here, this h nu, this is basically given as this will be equal to, so rho g h nu is basically the pressure difference between these two heights. Basically the pressure difference between these two heights, rho g h nu is equal to p1 minus p2. Okay, so that is the equation which you can put in here. We'll make it rho g h v is equal to half rho v2 square minus v1 square. Okay, that implies v2 square minus v1 square is equal to 2g hv. So by the continuity equation, we have a1 v1 is equal to a2 v2. Let's mark this as 1. So a1 v1, so by continuity equation, the amount of volume which is entering here is the amount of volume which is exiting here. So a1 v1 equal to a2 v2. So from this we can find out, we can say that v2 is equal to a1 v1 by a2. This second equation we can put in 1, so putting 2 in 1, we have a1 v1 by a2 square minus v1 square is equal to 2g hv. So by putting equation 2 and equation 1, we get this formula. So by going forward, by solving this formula, we have b1 square multiplied by a1 square minus a2 square divided by a2 square is equal to 2 hvg. That implies v1 square, v1 is equal to square root of 2 hvg 2 hvg a2 square divided by a1 square minus a2 square, a1 square minus a2 square. Okay, so this is the formula for finding out the velocity v1. So to find this velocity, what all do we need? We need the height difference, which is this one, which can be visually visually seen. Once the flow starts in the tube, we can visually see this difference in the height. If it is a fluid, you can see this visually. Okay, if it is um, yeah, if it's a fluid, you can clearly see this difference. And then If it's not a fluid, there is a way. It's called as a pitot tube. In that, I will show how, if you want to measure air and it is not visually visible on the Venturi tube, that height difference, how can you measure it? Okay. So then you have g, which is the acceleration due to gravity, a2 square, a1 square, both of them are known to us. Okay, so this formula, which is pretty straight. So this formula is pretty straightforward after that. So V1 is equal to square root of 2 HVG A2 square by A1 square plus A2 square. The full square root of this. So this will give us the velocity. Now you can see how intuitively this Venturi tool can help us to measure velocity of fluid flow. This can help us to measure the velocity of the flow velocity.